Hello everyone, my name is Mohammed Tawfiq, and today we will explore the pivotal role of germanium in modern optoelectronic and photonic devices. This presentation for Engineering Science, EMJ 12002, will delve into why this often overlooked element is a cornerstone of next-generation technology. Our story begins not in a modern lab, but in 1886 with the German chemist Clemens Winkler. While analyzing a rare mineral, he discovered a new element. This discovery was remarkable because its properties had been predicted 15 years earlier by Dmitri Mendeleev, the father of the periodic table. Mendeleev had left a gap in his table for an element he called ecosilicon, foreseeing its atomic weight and density with incredible accuracy. In honor of his homeland, Winkler named the new element germanium, from the Latin word Germania. Initially, germanium was the star of the semiconductor world, powering the very first transistors. However, silicon, being more abundant and stable at higher temperatures, soon took over, pushing germanium to the sidelines for several decades. But as we'll see, its story was far from over. So, why is germanium making such a significant comeback? The answer lies in light, specifically infrared light. Our modern world runs on data, and that data travels as pulses of light through vast networks of fiber optic cables. These systems primarily operate at specific infrared wavelengths, namely 1310 and 1550 nanometers, where signal loss is minimal. Germanium possesses a unique and highly valuable property. It's transparent to this infrared light. This transparency, combined with its excellent electronic properties, makes it the ideal material for detecting and manipulating these light signals. Furthermore, germanium can be integrated directly onto silicon chips, a field known as silicon photonics. This allows us to create powerful, compact, and cost-effective devices that merge the processing power of electronics with the speed of photonics, right on a single chip. From the massive data centers that power the internet to the future of high-speed communication, germanium is the unsung hero enabling this technological revolution. To truly understand germanium's capabilities, we must examine its fundamental material properties. Physically, germanium has a diamond cubic crystal structure, similar to silicon. However, its lattice constant, the distance between its atoms, is about 4% larger. This slight mismatch is a critical challenge in manufacturing, but as we'll discuss later, engineers have developed clever techniques to overcome it. Mechanically, germanium stands out due to its high refractive index, which is its ability to bend light. This property is essential for guiding light within the tiny waveguides of a photonic chip. It's also remarkably tolerant to strain, meaning it can be stretched or compressed without breaking. This allows engineers to deliberately apply strain to fine-tune its electronic and optical properties, a technique known as strain engineering. Thermally, germanium's conductivity is lower than silicon's. This means it doesn't dissipate heat as effectively, which can be a concern in densely packed, high-power devices. Managing heat is therefore a key design consideration for any germanium-based component. Perhaps most importantly are its electrical properties. Germanium has a narrow bandgap of just 0.66 electron volts, compared to silicon's 1.12 electron volts. This smaller energy gap is precisely what allows it to absorb the low-energy photons of infrared light used in telecommunications, something silicon cannot do efficiently. Additionally, germanium boasts exceptionally high carrier mobility. This means both electrons and their positive counterparts, holes, can move through the material much faster than in silicon. This high mobility is the key to creating ultra-fast photodetectors and other high-speed electronic components. When we compare germanium and silicon side by side, we see they aren't competitors, but collaborators. Each has unique strengths that, when combined, create devices more powerful than either could achieve alone. These unique properties translate into a wide array of cutting-edge applications in optoelectronics. One of the most prominent is in high-speed photodetectors. Thanks to its high carrier mobility and strong infrared absorption, germanium photodetectors can operate at speeds exceeding 100 gigahertz. This is crucial for next-generation telecommunication systems, including the development of 6G, which will demand unprecedented data rates. These detectors are the eyes of our fiber optic networks, converting light-speed data back into electrical signals inside data centers and network switches. But germanium isn't just for detecting light, it's also learning to create it. For years, a major goal of silicon photonics has been to create an efficient, on-chip laser. Pure germanium is an inefficient light emitter, but by alloying it with tin, researchers have created a new material, germanium tin, that can function as a direct bandgap semiconductor. This breakthrough has led to the development of the first germanium-based lasers that it can be fully integrated into a CMOS-compatible silicon platform, paving the way for complete photonic integrated circuits. Beyond telecommunications, germanium is enabling new frontiers in sensing. Its sensitivity to the mid-infrared region of the spectrum is particularly useful for detecting the unique absorption signatures of various chemical and biological molecules. This has led to the development of compact lab-on-a-chip systems for environmental monitoring, medical diagnostics, and industrial process control. These miniature sensors can provide real-time analysis, replacing bulky and slow laboratory equipment with a single powerful photonic chip. A key driver of germanium's success is its compatibility with existing manufacturing infrastructure. The processes used to create germanium on silicon devices are largely compatible with the standard CMOS fabrication techniques used for virtually all modern microchips. This allows for large-scale, cost-effective production without needing to build entirely new factories. To overcome the lattice mismatch between germanium and silicon, engineers have developed innovative methods like aspect ratio trapping. This technique involves growing germanium inside very narrow, deep trenches etched into the silicon. The trench walls effectively trap the defects that arise from the mismatch, allowing a layer of high-quality, defect-free germanium to grow above them. From a sustainability perspective, germanium also presents advantages. It is a non-toxic element, making it safer to handle in manufacturing and dispose of at the end of its life cycle. Furthermore, recycling processes for germanium are well established, primarily driven by its use in fiber optics and infrared optics manufacturing. The energy efficiency gained by using germanium photonics in data centers is also a significant environmental benefit. By replacing electrical interconnects with light-based ones, we can drastically reduce power consumption and cooling requirements, leading to greener and more sustainable data infrastructure. This exploration has been a journey of independent learning, taking me far beyond the scope of traditional textbooks. Understanding the intricacies of defect engineering and bandgap tuning reveals the elegance of materials science in solving real-world problems. Discovering the transition of germanium from a historical footnote to a key enabler of modern technology has been particularly inspiring. It highlights how scientific principles are not static, but are constantly being reapplied in innovative ways. For my future engineering career, this project has solidified the importance of an interdisciplinary mindset. The convergence of materials science, electrical engineering, and physics in silicon photonics is a perfect example of how complex challenges require collaborative and multifaceted solutions. In conclusion, germanium stands as a critical bridge between the worlds of optoelectronics and photonics. Its unique properties make it an indispensable material for the high-speed communication systems that form the backbone of our digital society. As we look towards the future of technology, from 6G to advanced sensing, germanium will undoubtedly continue to be at the forefront of innovation. Thank you for your attention.